Okay, so welcome everybody. Thank you again. Welcome to the third day, the contributed talks. It is my great pleasure from CIMAT, and she's going to be talking about stationary fully non-linear mean field games.
Hello everyone. Okay, sorry. Hello everyone. Thank you, Danielle, for the nice introduction. I also would like to thank the organizing committee for this opportunity and everyone for showing up. It's a great pleasure for me to give this talk. Today I'm going to talk about stationary fully nonlinear mean field games. This is a joint work with Edgar. The first thing I would like to point out here is stationary fully nonlinear mean field games. They name it, we call it stationary because it does depend on time, okay? Now I'm going to introduce the problem. The first thing we consider is the system here, where the first equation is the is f of h of u equals to n power to 1 over p minus 1 in b1, and the derivative with respect to xi, xj with this function equal to 0 in b1. Here, f is a fully nonlinear elliptic operator. That means there is this two constant, lambda and capital lambda, such that for all symmetric matrix, we have this estimate here for all and non-negative. And at some point, we need to assume the growth condition on f is pretty much similar to the elliptic condition, but instead of we asking for every n non-negative, we ask for all we allow this estimate here for every matrix of symmetric matrix, okay? And Fij is the derivative of f with respect to the I and j of the m, and m is an integrable and non-negative function in B1. Okay, the source term here is an integrable and non-negative function. We call this system is a mean field game. Because it has a joint structure. That means the second equation is a formal adjoint of the first, the linearization of the first. Now, I would like to explain what happened when you have the growth condition. If f is an elliptic operator, lambda elliptic operator, we know that f belongs to this bow tie here. But when you have the growth condition, the first quadrant here is the same, but the third quadrant will reflect in the second one. It's what happened when you have the growth condition. Now I would like to summarize what the results that we get for the fully nonlinear mean field games. The first one is gains of integrability, and the probability of regularity. Then we prove existence of solution. And without convexity, we prove by relaxation methods properties about the minimization energy. And at last but not least, we give an example in dimension 1. Okay. Okay. I think it's a natural question to ask, what are MIFID games? Well, MIFID games are a model that we study strategic interaction involving a very large number of players. This kind of models was introduced circa 2006 for Las Lyons. And the initial approach for this kind of models was analyze a master equation. And when you have the assumption as independent of Brownian motions, these models, the master equation reduced to the coupling of a Hamilton-Jacobi and a Fokker-Planck equation. And there is plenty of results in this topic that I would like to summarize some. And the extent and uniqueness of solution, regularity, probabilistic developments, numerical methods, obstacle problems, applications to life and social science. And okay, I think it's a good time to give a definition for our solution. A solution to our system. Pair UN is said to be a weak solution to this system if satisfies some conditions. First, U is continuous in B1, and the M is integrable in non-negative function in B1. The second, U is a viscosity solution to the first equation of this system, and M is a weak solution to the second equation. That means M satisfies this equation for every phi safely in compact support in B1. Okay. Now I'm going to present the first result that we prove. The result is about the gains of regularity for the double divergence equation. The second equation is no double divergence equation 2, because we take two derivatives there. Okay, and then okay, the gains of these results is let M be integrable function, non-negative weak solution to the second equation. Suppose F is an elliptic operator, then we have that M belongs to LED of D minus 1 locally in B1, and there exists a constant that we can estimate the norm of M in this space. Notice that we have here a gain of integrability because if we write D minus 1, we know that D minus 1 is less than D. When we divide both of sides for D minus 1, then we get that U1 is less than D over D minus 1. Okay, okay. The proof of these results is based on the Phelps Stokes works in the Duke Mathematical Journal. We noticed that in this work, Phelps and Stokes use the condition, using the fact that the coefficients are smooth. In our case, we only needed we only need the coefficients be bounded. And okay, once we have gains of integrability, we would like to show improved regularity results. And now I'm back here. Okay. When we study this equation here, and the M belongs to L1, we know by regularity results that the regularity of the U, the regularity of the solution of this equation, is in W to P minus 1, okay? But when you have the gains of integrability, we can get improvement of regularity. Let U be a solution of this system. Suppose F is an elliptic operator convex with respect to M. Then we have U belongs to W2 D times P minus 1 over D minus 1 in B1 locally. And we have estimate for U and this norm here. Okay. Okay. Now, as you can see, this graph represents the gains of irregularity. The first thing we have to notice here is when M belongs to L1, we have this regularity here, as I said before. When we study this system with the gains of integrability, we have the whole gain of this curve here. They represent the gains of regularity. Notice also when G goes to infinity, we have the regularity here, the regularity of the function U approach to the regularity that we already know. Okay, is a natural question to ask. When we have the regularity in Sobolev spaces, is if it's possible to produce regularity results in Hölder space. The answer for this question in our case is yes. We can by embedding Sobolev embeddings have the irregularity in Hölder spaces. Okay. Let U be a weak solution to the Mifford game. Suppose F is a lambda elliptic operator with n convex. Suppose for the P minus 1 greater than G, then we have that U belongs to C1 alpha star locally for this alpha star here. And we also have estimate for the U, the norm of U in this space. The proof of this result is using Sobolev's embedding, okay? Now here we finish the irregularity results that we have. Then we are talking about the existence of solution. Okay, we investigate the existence of a minimizer. I, where I of U is equal to this integral here. And we investigate the first we investigate the existence of solution of the minimizer and the set here, where A equals to U in W2PG, U convex, with J in W2P, B1 convex. Here, the set is the functions U that belongs to W2P that is equal to G and the boundary, G and the boundary. We notice here this functional, the Euler-Lagrange equation that we produce our system is from this functional here. Okay. Now, since we want to prove the existence of a minimizer, we have to make sure we have two properties. The first one is coercive condition, and we notice that since F is a lambda elliptic operator, and we are in search for minimizing this set where U is convex, we have the coercive condition. That means we have this functional bounded by below. And we also produce a second property that we need to prove the existence of a minimizer, that is weak lower semi-continuum in this result. Suppose F is a lambda elliptic operator, convex with respect to M. Let UN in A be such that we have this weakly convergence here, then we have the property that we want. Notice here that in this case, since the functional only depends of the Hessian, we only need this weakly lower convergence. Okay. Okay. Once you have the coercivity condition and weakly lower semi-continuity property, we can prove the existence of minimizing. Suppose F is elliptic operator convex with respect to M. There is this U star in A such that U is the minimized for every U in A. Okay. The first thing we notice here is this minimized. We have a minimizing the set of the convex function because A is the set of the convex functions, but there is no reason for this minimize to be a critical point in W2PG, okay? Then at this point, we assume the condition, the growth condition in F, and this condition allow us to produce the existence of a critical point and existence of minimizing, okay, in the whole space. This is a content of this theorem. Suppose F is a convex operator and satisfies the growth condition. There exists a minimizer U star in the whole space for I. In addition, this minimizer produce a solution. This minimizer produces a solution that is minimizer for this system. Okay, these are that you already said. And we use the regularity results to show that this solution, it will produce a solution to this system. Okay. Now, without the hypothesis, the convexity hypothesis on F, we would like to study what happened when we don't have convexity on F. And when we study this kind of when we have this approach, we call this approach relaxation method. When you jeopardize the convexity, we call the relaxation method. The first thing we have to do here is consider the relaxed problems. The relaxed functional, where I bar of U is given by this integral here. The first thing we notice here is we have here, instead of F, we have gamma F. Okay, where gamma F is a convex envelope of F, is defined as usual. Okay, and the first property that we proved for the relaxed problem was to ensure that we have the coercivity property for the envelope convex. Okay, once we have this property, we prove we have the same for the I bar. Okay, and then we get this result here, that we get a connection between I and the I bar, and the following. Suppose F satisfies a growth condition, then there exists UN in W2PG such that I of UN converges to I bar U star, and we also have that UN, the sequence ring UN, weakly converges to U star in W2P, where this U star here is a minimizer of I bar. Okay. this is the last theorem. This is the best results that we can get when we jeopardize the convexity hypothesis on F, the operator F. Okay. Now, I would like to present the last but not least. I would like to present the example in dimension 1. Here we consider P greater than 2, and we consider F 0, 1 in R, and the F given by this. We notice after calculations that the second derivative of F might be negative because depending on the value of Z and P, and the F might fail to be differentiable when we, okay. And now we have the operator. The first thing we obtain is the functional associated with this operator. This one here, and then we reproduce the results that the same work that we did before. We produce the fully nonlinear mean-field game associated to this functional by doing a Euler-Lagrange equation, and then we define similar to the general case. Then we got the system here, and then we prove two results in this case. If F, let F be 1 plus C power P power over P, then we have a solution for this system in dimension 1. Ux is given by this, U of X, E and M is given by this, where A, B, and C and D are real constants. And then we prove that a minimized solution for that system is a affine function and a uniform distribution, okay? Where A star and B star are real constants. What we've done so far, in the regularity results, first we produce gains of integrability. Then we produce an improved regularity in Sobolev space, and we prove regularity in Hölder space. In the convex setting, we prove existence of minimizer for the functional, and then we prove the existence of solution for the mean-field game system. Without convexity hypothesis on F, we still get information about the minimization of the energy, okay? And then we explicit solution in dimension 1. Thank you very much for your attention. I think I'm finished here.
Okay, thank you very much, Pêdra, for the very interesting talk.